We've been talking about different methods for taking derivatives over the last couple weeks, and now we're going to start looking at a couple of applications of the derivative, specifically linearization and differentials. Both of these are techniques which are used often in business, for example, and economics, when we want to come up with an easy way to estimate the value of a function, maybe a function that's quite complex, and we use the derivative and the small changes that can happen in the tangent line to estimate what's happening in on a complicated function. In our examples, we're going to use functions that we know so that the math is not too challenging. In these pictures, we are looking at a tangent line to curve we've talked about a number of times, x squared. And we can see that at the point 1, 1 in this first picture here, we know that if we took the derivative of x squared, we get 2x. And then using the point slope formula, we'd be able to get this equation for the tangent line. This second picture on the right is the same exact graph, but it's just zoomed in a little bit closer. And then same thing with these other pictures down here. Each time we're zooming in closer and closer to the function. And what you're supposed to take away from these pictures is that the more we zoom in this very small neighborhood around the point 1, 1, the tangent line actually becomes a fairly good estimate of the function. So even if we don't know, let's say, a point 1.001 for our x value, if we don't know what the y value would be if we plug that into the function, we could use the tangent line to estimate that function value. And it's often easier to plug values into a tangent because it's a straight line, and the function, the way the function is written is fairly simplistic. So this is an example of what we call linearization, kind of putting into math terms what I was just talking about. This really is just a different way of writing the equation of a tangent line. Let me show you how we get to this. So if we start with a function, say y equals f of x, and if we were to plug in a particular point, let's say at x equals a, the output value would be f of a. Right? So the point that we're talking about, the tangent line, would be at a comma f of a. The slope is going to be the derivative of that function that we started with. The slope would be f prime of x, taking the derivative. So I'm going to say that the tangent line at the point a f of a is going to be, again, using the point slope formula, y minus f of a. So this is y minus the y value. And then we put the slope, m, and then we do x minus a. So we've been using this formula tons of times in class. Y minus y1 equals m x minus x1. We're just plugging in these generic values. And if I add, in this version here, if I add f of a to both sides, you see that I get this equation here, which is the linearization. Oh, I forgot back here. Let's go back. Because we're actually evaluating the slope at the point A, we're going to put f prime of A. So again, what I've got highlighted here is the slope of the tangent line generically at any point on the graph, and we call that the linearization, the tangent line approximation that we can use to estimate a value on the function. So here's an example. I know that we can just plug in 0 and 3 into this function, but just expand your mind for a minute and pretend that this function that we're given is something really complicated, and that to plug values in might be costly. It might take a lot of calculation time on a computer. And so what we're trying to do is minimize the calculation time, minimize how taxing it is to a particular computer system, especially if we were going to calculate hundreds and hundreds of different values simultaneously. Um, and so this is what the application would be, that we want to know what's happening at x equals 0 and x equals 3 for some complex function. We're pretending that that complex function is the square root of 1 plus x. So I'm going to use that equation that we just had above. We're going to use this idea that the linearization of x is going to be f of a plus f prime of a times x minus a. This is just a modified version of the tangent line. So for the first example, we need to actually, let me move this down and make more room here. We're letting a equal 0. So a is equal to 0. And f of a, if we plug 0 into our original function, we're going to get 1. So the point that we're considering is 0, 1. We can see that on the graph here, right? The derivative of this function is, well, let me actually rewrite this first. Let's write f of x instead as 1 plus x raised to the 1/2 power, so we can use the power rule. So f prime of x is going to be 1/2, and then we'll drop the power down by 1. Oops. 1 plus x to the negative 1/2. Technically, I need to use the chain rule and multiply by the derivative of the inside here, but that's just going to be a 1, so I don't need to worry about that. So our slope here, f prime at a, at the point a, well, let me write this more succinctly first, will be 1 over 2 times the square root of 1 plus x in the denominator there. So what would this be if I evaluated at the point 0, 1, right? A is equal to 0 for r. So we're just going to have 1/2. If I put 0 in here for x, I'm just going to get 1/2 for our slope. All right, so I think I've got all the components that I need. Again, let's grab this formula up here, copy that, and bring it down here. Okay, so this is what we're going to use for our function. So we're going to say that L of x, or yeah, is going to be f of a, we said was 1. That's up here. F prime of a, that's here when we plugged in a, was 1/2. And then x, a is equal to 0, so we're just going to have x. So it looks like the tangent line that will approximate the function in areas near 0 is going to be 1 plus 1/2 x. Let's repeat that same idea, but instead this time we'll use the point x equals 3. So we know that the derivative in general, we just found the derivative. It was 1 over 2 times the square root of 1 plus x. So the derivative at 3 would be, let's see, 2 square root 4. This is going to be 1/4. If we plug 3 into the original equation there, we're going to get 2. So this is our slope, and this is the point is going to be 3 comma 2. So again, looking at this formula here that tells us what the linearization is going to be, paste this over here, and I'm going to make a little more room. The linearization for the function close to x equals 3 is going to be, well, let's see, when I plug the original point in, when I plug 3 in, I got 2, so that'll be 2. F of a is 2. The derivative at a was 1/4, and then x minus, we're plugging in 3 this time. All right, so L of x is, let's see, it'll be 1/4 x, and then I'm going to have 2 minus 3/4. Just grab a calculator, 2 minus 3/4, which is 5/4. Okay, so what does this mean? Let's look at both answers together. What we did is we did this problem twice. Let's see if I can get these together here on the same screen. There we go. This was in the neighborhood near x is equal to 0, and this was in the neighborhood near to x equals 3. You could say that this is the tangent line, right? That's the way that we've calculated this in the past, but we're just using different terminology because we're going to say we can use this line here to estimate the function values near to that point. So if I wanted to look at, let's say, x equals 0.001, or x equals 2.999, points that are very close to this, this would be a line that we could plug function values into and get an estimate for the function. And then this would be the one that would work for neighborhoods close to 0. So we're going to do an example here where we're going to use the linearization to estimate the function value of cosine of 1.5. Now, if we take pi over 2, and in decimal form is about 1.57, yada, 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 going on because it's an irrational number, right? So we're going to use what we know about the cosine of pi over 2 to estimate what the cosine of 1.5 is, given that these two values are pretty close together. So first, let's figure out what f of pi over 2 is. If we take cosine of pi over 2, we know that that's 0. So our point is pi over 2, 0. The derivative of cosine is negative sine. And if I evaluate that derivative at pi over 2, we get negative 1. So in this example, A is pi over 2. So our linearization is going to be this. And again, we're taking a as pi over 2. So when we plugged the function in, when we plugged pi of 2 into the function, we got 0. So put 0 here. The derivative at pi over 2 was a negative 1. And then we'll have x minus pi over 2. So it looks like the linearization will be negative x plus pi over 2. Okay. So how do we use this? To estimate cosine of 1.5, we're going to look at L of 1.5. We're just going to take 1.5 and plug it into this equation that we came up with. So we'll have negative 1.5 plus pi over 2. I'm going to put that into the calculator. And I get 0.070796. This is going on, but I'm just going to go out to here. So let's compare this to cosine of 1.5. I'm using this estimate above because if I didn't have, if calculating the cosine was really complicated, I could use this estimate above. Obviously, I can do both of these in the calculator, but you get the point. Make sure if you're doing this at home that you put your calculator into radians. So cosine of 1.5 is 0.070737. So we can see, oops, out a couple of digits. That's where the estimates are not correct, but within the 10,000ths, we have that the estimate is exactly the same. So again, the point is that we can use this linearization, this formula that's much simpler to estimate the function values at a particular point. Similar concept, but just with a different name, is called a differential. And this is a picture version of kind of what we've been doing in the last couple problems. The easiest way to explain this equation is that if I take the derivative, another way of writing that is dy dx, and we've just moved dx onto the left side there, right? dy is called a differential and dx is called a differential, and we mean them to be small changes in the x and the y directions. So dx is this, and dy is this. And so looking at that tangent line, when I make small changes in y, I can see that the function value and the value of the tangent line, yeah, there's some difference there, but depending on how close I make delta x, if I move delta x closer and closer to A, well, now the distance here isn't as far. So in very small neighborhoods, that tangent line, that linearization, is a good estimate for the function. Here's an example, again, one that we could just do by straight calculation, but it's just meant to show you the idea. We have a circle that had a radius of 10 meters, and we're increasing it to 10.1. And we want to use the differential of the area to estimate the increase in the circle's area. So we'll first do this using differentials, and then we'll compare what the actual answer would be if we calculated it on its own. So we're going to use the formula A equals pi r squared. And the formula for differentials is going to be dA is equal to A prime of A dr. This is just taking that formula that we had up here and just changing the variables to be A for area and R for radius. In this case, A is going to be 10. And dr, the change in radius, is going to be 0.1. What's the derivative of the area? Here we would have 2 times pi times r. I just used the power rule. Bring the 2 down into the front and drop the power on the radius down by 1. Okay, so I'm going to plug in what I have. dA is equal to, all right, for the derivative, 2 times pi times a. What I did is I put a here instead because we're taking the derivative at the point A. And then dr, plugging in what we know, 2 pi, a is 10, dr is 0.1. So it looks like we think that the change in area is going to be about 2 pi meters squared, right? Because we're talking about an area. So the area for the original radius plus the change in the radius is going to be approximately this. The area that we could calculate with 10 being the radius, and then this differential that we just calculated. We think that the estimate in the change, as the radius changes by 0.1, we think the estimate change for the area is going to be about 2 pi. So A of 10 is pi times 10 squared. And the estimate for the change in area we think is going to be 2 pi. So our approximate answer for the new area is 102 pi meters squared. What's the actual area if we were to calculate it? 10.1. It would be pi times 10.1 squared, which is 10.1 squared, 102.01 pi meters squared. Pretty close estimate, right? These two are pretty close together. For our last example, we're going to calculate a cube root. Cube roots are pretty difficult to estimate unless you have a calculator that can do this. And so this would be a good example of one that it's really hard to find the cube root if you don't have a high-powered calculator. We know that the cube root of 8 is 2, so we're going to use 8 as kind of the number that is something we already know about, and we're going to estimate something close to it. So the function we're considering is x to the 1/3 power. And if we take the derivative here, let's see, we'll have 1/3 x to the -2/3. So this is 1/3 times x to the 2/3 dx, right? Okay. So we're going to let a equal 8, and we're going to let dx equal -0.03, the difference between 8 and this 7.97. So we think that the estimate of 7.97 being plugged into the function, taking the cube root of it, is going to be taking the function value and adding on that difference, or in this case, subtracting. And the approximation for that is the function plus the change in y. So 8 to the 1/3, we're using something we already know. And then we're using that differential that we just found. So this will be, again, I'm going back up here, and I'm going to put 1/3. This will be 8 to the 2/3. And then dx is the negative 0.03. Okay, plug this into a calculator. So we have 2 plus, this is going to be 1/12. Let's see, 2 plus 1/12. I'm getting 1.9975, and this is our estimate. Because I have a calculator that can actually handle this, I'm going to plug this in to get the true answer. Oops, 1/3. Just for comparison. And I'm getting 1.997496. Pretty good estimate, right? Here, the answers are different, but if I round it up, I'd get the same answer. So again, don't get too hung up on the fact that we're using functions that we actually know how to plug into a calculator. The idea is that we're using functions that we know something about to show the process of what differentials are used for. We will go over more examples in class, and I